digital photography and video editing has been known to all of us. Some of the things that they're working on now will absolutely blow your mind. To help me talk about some of the things in the future, if I could have David Sellison come up. He is the head of research at Adobe, and also Dr. Todor, Georgia, fellow at Adobe. David, tell us about the thing that you guys have been working on.
All right. Well, I wanted to start by telling you that I had some amazing experiences earlier in my life where I had the opportunity to travel to places that I probably won't ever get back to. Probably they don't even exist the same way today as they did back then. I remember being up in the hill tribes in northern Thailand and being surrounded by children who had never seen a Westerner before. And of course, I brought a camera along. It was a film camera back then, and I was very proud. It was very cute. It was little. It was inexpensive, which was important to me back then. And I took lots of pictures. But when I got home, I found out that it wasn't a very good camera that I had brought along, and pretty much every single picture I'd taken on that trip was blurry, out of focus, not focused on the thing I wanted. Big disappointment. So many of you out there may not remember this, but once upon a time when you took pictures on film. And you had to wait and get the film developed to find out how things came out. And it turned out that whatever you did at exposure time, you were pretty much stuck with. It was exactly the focus that you took, it was the exposure that you took, it was the color balance that was on the film that you took the photograph on. With digital photography, which many of you probably have been using much of your lives, you have a lot more choice right then and there when you take the picture, and even after the fact. You can check and see how the exposure is doing, how the focus is doing. You can go back and change the exposure and so on. If you got the focus wrong, though, which is something that you can't really see on those small screens, there's not a whole lot that you can do about it.
And it kind of defines the point about a snapshot in time.
Yes.
You capture that snapshot in time, and that's it.
That's right. So what we want to do is start capturing more of the whole moment, the whole experience at that time. And then later, you can go and make whatever adjustments you need. And one way to think about this is that resolutions have been increasing on and on and on in sensors. And now they're at the point that they're beyond what you really need for most prints. On the other hand, you can take advantage of that extra resolution by capturing more information on the sensor. And at Adobe, we've been experimenting with this. So you can see, well, I can see down here. I don't think you can see up there.
Oh, let's go back to the intro slide,
title slide, actually. You can see one lens that Todor put together, which was an initial prototype. And what it does is it allows you to capture...
What do you call those, David?
They're called a planoptic lens.
It's a planoptic lens.
And what it does is it allows you to capture multiple views of the scene from slightly different viewpoints. And if you have a high-resolution sensor, each one of those images can be a fairly high resolution. And the neat thing is that with software, with computation, you can actually put this together into one large, high-resolution image. Now, since then, the technology has evolved a bit. Todor has been experimenting with micro-lens arrays. They're actually mounted instead of in front of the lens, they're behind the lens and close to the image sensor. They work better in some ways.
So that's interesting. Instead of taking one image of the subject, you now have a whole bunch of little lenses.
Right. A whole bunch of little lenses.
And they all see the subject from a slightly different view.
And they each get like a part of the subject. And then with software, you can put all those different parts together. In a sense, you're capturing a whole 4D light field. It's 4 dimensions in the sense that you've got sort of 2 dimensions of the spatial position of the light ray, and then you have also 2 dimensions of the orientation of the light ray. So with that 4D image, you can then, after the fact, use computation to take the place of optics. And so with computation, you then have a lot more flexibility. So at the time that you're going to view the picture, you can actually change the vantage point, the viewpoint a little bit, and you can also change the focus.
That's interesting. Instead of one ray per pixel, you're now capturing a lot of different rays for that very same pixel.
Right, they're independent rays showing how the light came in from all different angles at that pixel.
Now, what's the complexity of the mathematics that is to resolve that?
Well, it turns out that to resolve that, to take these individual little pieces of an image and put them together into one large image from any arbitrary view with any arbitrary focus. Turns out that texture mapping hardware is exactly what you need to do that. That is just the right approach. And so using NVIDIA chips is just a perfect way to go. We've been able to get speed-ups over, well, speed-ups over CPU algorithm about 500 times.
Wow. That's unbelievable. So if I were to take one picture then of a planoptic lens with all those micro lenses, and I wanted to turn that what we saw earlier, maybe we could change now.
Yeah, we can change
to what Todor has on his workstation here.
Right. So what you're seeing here is the image, the raw image that the sensor captured from a micro lens array that's mounted behind the main lens of the camera. And if Todor zooms out, why don't you zoom out actually? Well, all right. If you zoom out, you'll see that you can kind of make out actually what this is. It's a photograph of a girl taking a picture in front of some blue thing. It's hard to see exactly. If we zoom in, we'll see exactly what that raw data is. It's lots of tiny little pieces of image. And each one is from a slightly different vantage point. And together they comprise the whole image from all those different directions.
Now suppose I wanted to use, I'll just use, and when you guys first started doing this research, you just ran it on a cluster of CPUs.
That's right.
Right, because at the time, a programmable GPU wasn't really available yet. Right. And so if I were to just take this image and I wanted to figure out a way to now distill out a photograph, what would it take?
Well, with our earliest algorithms, it was about an hour to do it. Then we were able to improve the algorithms, and then it was more like a minute or so. But now, in 120 hertz, we can be producing these views.
No kidding. Well, Todor, show it to us.
All right. So
this is a dump of basically the sensor.
That's right. That's just the raw sensor image. And here now is the image put back together again. Now you can see this is like the photos I took in Thailand that unfortunately the image is focused on the wrong thing. But the beauty is that with computation, we can now refocus in real time on anything at all. So pull the girl in.
David, that's magic.
This is one of the most common problems that people have with photographs, is they're unhappy with the focus. There's nothing they can do about it.
So I could literally refocus it on wherever I want to refocus it on. Well, I guess, with some limits. So now you're focusing it on the branches on the tree.
That's right. And now he's going all the way toward the girl, and you can go all the way back again toward those are beehives there. I put those in focus.
That's unbelievable.
See all those different levels.
Now, of course, this is just one demonstration of the capability of planoptic lens coupled with a massive amount of image processing that comes along with parallel computing. But there's all kinds of algorithms you guys could invent in the future that takes advantage of having captured the radiance of the entire scene.
Yes. Right? So we'll be able to do things like high dynamic range. We'll be able to do things like, if there's motion in the scene, being able to get rid of some of the motion blur. Or if there's motion in the camera, getting rid of the motion blur there. If you do this in video, obviously it opens whole new possibilities for cinematographers to be able to be creative after the fact.
So well, speaking of,
because we're capturing the radiance, the four-dimensional radiance, or four-dimensional plane optic function, or light field, these are different terms, but because we are capturing this huge amount of data, we have huge amount of power, and those include many different modalities, not just 3D, not just refocusing, not just lens correction, HDR, and many others. So
what's interesting is that so far, digital photography has been really just about digitizing what used to be an analog process.
That's right.
And even with the current state of technology, once you've digitized it, you could still use Photoshop and all kinds of interesting algorithms to enhance.
That's right.
Clean up that
digitization is just the first step, and then computation gives you a lot more creative freedom.
And now, if we're able to capture much more of the world information using this planoptic lens, using radiance, capturing the radiance of the scene, now all of that raw data is available to us. When applied Photoshop to it, you'll be able to do something completely magical.
Yeah. Essentially, what we are doing, we are moving some of the optics, or essentially moving the optics into the computer. So now our focusing device, our camera, is inside the